Welcome back. You recently completed your capstone final submission and presentation, which is a massive milestone. Now we are shifting gears into the Ethereum fundamentals track. We'll be starting the Introduction to Ethereum Architecture course, specifically kicking off the module on understanding Ethereum's core infrastructure. Oh, and before we begin, this video is produced by Forge College. Today's lesson is on Ethereum core components and roles. If the network has ever felt like a mysterious black box, we're going to peel back the exterior and see what's actually humming inside. People often talk about Ethereum as if it's a magical, formless cloud floating in the sky. In reality, it is a physical network made up of thousands of individual computers running specific software. We call these individual computers nodes. To understand the entire global network, you really only need to understand one single node. You can think of an Ethereum node as a highly organized factory. It has a receiving dock, a strict processing assembly line, and an output desk. By learning how this single factory processes information, you can accurately predict how the entire global supply chain works together to secure billions of dollars without needing to trust a central authority. Let's look at this flowchart diagram to see how data moves through the factory. Stage 1 is the peer-to-peer layer, or P2P layer. Think of this as the factory's loading dock. Outside peers drive up and drop off raw data blocks and new transaction requests. Next, those requests move to the transaction pool, often called the TX pool. This is simply a waiting room. The raw boxes sit here temporarily, stacked up and waiting for their turn to be officially processed. Before they get far, they hit the validation queue. This acts as a strict inspector. It checks digital signatures and confirms the sender has a big enough fuel budget to pay for the work. It filters out obvious junk right at the door, so the factory doesn't waste energy on broken requests. Valid requests are sent to the execution engine. This is the heavy machinery. It crunches the math, executes the code inside the transactions, and officially updates the financial balances and data. Working right next to it is the consensus engine. This department is entirely focused on the sequence of events. It orders the blocks and enforces the rules that ensure this specific factory's output perfectly matches the output of every other factory on Earth. Once a transaction is executed and the sequence is agreed upon, the results and digital receipts go to the state store. This is a massive wall of filing cabinets where the permanent records are kept safe. Finally, we reach the responder stage. Imagine a front desk clerk. When outside users run queries asking for data from the files, the responder retrieves it from the cabinets and hands the answer back out to the world. This strict, segmented assembly line prevents bad data from crashing the computer. It ensures anyone, anywhere, can run this software and independently verify the truth without relying on a central authority. Now that you know the pipeline, we need to talk about the type of factory you choose to build. Not everyone has the money or hard drive space to run a massive data center. Because of that, Ethereum software can run in 3 different configurations, known as node roles. First is the full node. Think of this as your standard, reliable middle manager. It validates everything currently happening on the network today. But to save space, it throws away very old scrap paper, a process called pruning. Full nodes are the backbone of the entire network. They offer a highly secure way to verify the chain yourself without requiring thousands of dollars in commercial hard drives. Next is the light node. Imagine an intern working entirely from a smartphone. A light node doesn't store heavy data or execute complex math. It just scans the high-level summaries on those clipboards and asks larger nodes for cryptographic proof when it needs specific details. It trades local storage for a reliance on its peers. Finally, there is the archive node. This is the ultimate digital hoarder. It keeps a permanent record of every single state change since the very first block was created. These are massive, they are expensive to run, and they take weeks to organize and index. The network thrives because of this diversity. We need archive nodes for deep historical research, full nodes to maintain daily security, and light nodes so everyday laptops and phones can interact safely. Let's put this into practice. Say you are building an application that needs to check a specific smart contract balance from exactly 3 years ago. You route that request to your newly synced full node. You will almost certainly get an error. Why? Because the full node uses a pruning strategy, the front desk responder simply doesn't have that 3-year-old paper in its filing cabinets anymore. To get that specific historical receipt, your app has to route the request to an archive node. Knowing the responsibilities of these roles prevents you from wasting hours trying to fix a network failure when the issue is actually just a storage choice. When we zoom out, decentralization is just a coordinated ecosystem of these different nodes. They use their specific intake docs, execution engines, and storage pipelines to constantly gossip and verify data together. But how exactly do they find each other to share those boxes of data? That brings us right to our next lesson, peer-to-peer networking and synchronization. This video was made by Forge College. If you want to explore this subject further as an educational resource or dive deeper into other Web3 subjects, please visit our website at forge.college. See you in the next lesson!